John von Neumann. John von Neumann, /ˈnɔɪmən/ Hungarian, Neumann János Lajos, pronounced, December 28, 1903, February 8, 1957, was a Hungarian-American mathematician, physicist, computer scientist, and polymath. Von Neumann was generally regarded as the foremost mathematician of his time and said to be the last representative of the great mathematicians, a genius who was comfortable integrating both pure and applied sciences. He made major contributions to a number of fields, including mathematics, foundations of mathematics, functional analysis, ergodic theory, representation theory, operator algebras, geometry, topology, and numerical analysis, physics, quantum mechanics, hydrodynamics, and quantum statistical mechanics, economics, game theory, computing, von Neumann architecture, linear programming, self-replicating machines, stochastic computing, and statistics. He was a pioneer of the application of operator theory to quantum mechanics and the development of functional analysis, and a key figure in the development of game theory and the concepts of cellular automata, the universal constructor and the digital computer. He published over 150 papers in his life, about 60 in pure mathematics, 60 in applied mathematics, 20 in physics, and the remainder on special mathematical subjects or non-mathematical ones. His last work, an unfinished manuscript written while he was in hospital, was later published in book form as The Computer and the Brain. His analysis of the structure of self-replication preceded the discovery of the structure of DNA. In a short list of facts about his life he submitted to the National Academy of Sciences, he stated, "The part of my work I consider most essential is that on quantum mechanics, which developed in Göttingen in 1926, and subsequently in Berlin in 1927 to 1929. Also, my work on various forms of operator theory, Berlin 1930 and Princeton 1935 to 1939, on the ergodic theorem, Princeton, 1931 to 1932. During World War II, von Neumann worked on the Manhattan Project with theoretical physicist Edward Teller, mathematician Stanislaw Ulam and others, problem-solving key steps in the nuclear physics involved in thermonuclear reactions and the hydrogen bomb. He developed the mathematical models behind the explosive lenses used in the implosion-type nuclear weapon, and coined the term kiloton of TNT, as a measure of the explosive force generated. After the war, he served on the General Advisory Committee of the United States Atomic Energy Commission, and consulted for a number of organizations, including the United States Air Force, the Army's Ballistic Research Laboratory, the Armed Forces Special Weapons Project, and the Lawrence Livermore National Laboratory. As a Hungarian émigré, concerned that the Soviets would achieve nuclear superiority, he designed and promoted the policy of mutually assured destruction to limit the arms race. Early life and education. Family background. Von Neumann was born Neumann János Lajos to a wealthy, acculturated and non-observant Jewish family. In Hungarian the family name comes first. His given names equate to John Louis in English. Von Neumann was born in Budapest, Kingdom of Hungary, which was then part of the Austro-Hungarian Empire. He was the eldest of three brothers. His two younger siblings were Michal, English, Michael von Neumann, 1907 to 1989, and Miklos, Nicholas von Neumann, 1911 to 2011. His father, Neumann Miksa, Max von Neumann, 1873 to 1928, was a banker, who held a doctorate in law. He had moved to Budapest from Pécs at the end of the 1880s. Miksa's father and grandfather were both born in Ond, now part of the town of Szerencs, Zemplén County, northern Hungary. John's mother was Kahn Margit, English, Margaret Kahn. Her parents were Jacob Kahn and Katalin Meisels. 3 generations of the Kahn family lived in spacious apartments above the Kahn-Heller offices in Budapest. Von Neumann's family occupied an 18-room apartment on the top floor. On February 20, 1913, Emperor Franz Joseph elevated John's father to the Hungarian nobility for his service to the Austro-Hungarian Empire. The Neumann family thus acquired the hereditary appellation Margitai, meaning of Margita, today Margita, Romania. The family had no connection with the town. The appellation was chosen in reference to Margaret, as was their chosen coat of arms depicting 3 Margarites. Neumann János became Margitai Neumann János, John Neumann to Margita, which he later changed to the German Johann von Neumann. Child prodigy. Von Neumann was a child prodigy. When he was 6 years old, he could divide 2 8-digit numbers in his head and could converse in ancient Greek. When the 6-year-old von Neumann caught his mother staring aimlessly, he asked her, "What are you calculating?" Children did not begin formal schooling in Hungary until they were 10 years of age. governesses taught von Neumann, his brothers and his cousins. Max believed that knowledge of languages in addition to Hungarian was essential, so the children were tutored in English, French, German, and Italian. By the age of 8, von Neumann was familiar with differential and integral calculus, but he was particularly interested in history. He read his way through Wilhelm Onken's 46-volume Allgemeine Geschichte in Einzeldarstellungen. A copy was contained in a private library Max purchased. One of the rooms in the apartment was converted into a library and reading room, with bookshelves from ceiling to floor. Von Neumann entered the Lutheran Fossori Evangelicus Gymnasium in 1911. Eugene Wigner was a year ahead of von Neumann at the Lutheran school and soon became his friend. This was one of the best schools in Budapest and was part of a brilliant education system designed for the elite. Under the Hungarian system, children received all their education at the one gymnasium. The Hungarian school system produced a generation noted for intellectual achievement, which included Theodor von Karman, born 1881, George de Hevesy, born 1885, Michael Polanyi, born 1891, Leo Szilard, born 1898, Denis Gabor, born 1900, Eugene Wigner, born 1902, Edward Teller, born 1908, and Paul Erdős, born 1913. Collectively, they were sometimes known as the Martians. Although Max insisted von Neumann attend school at the grade level appropriate to his age, he agreed to hire private tutors to give him advanced instruction in those areas in which he had displayed an aptitude. At the age of 15, he began to study advanced calculus under the renowned analyst Gábor Szegő. On their first meeting, Szegő was so astounded with the boy's mathematical talent that he was brought to tears. Some of von Neumann's instant solutions to the problems that Szegő posed in calculus are sketched out on his father's stationery and are still on display at the von Neumann Archive in Budapest. By the age of 19, von Neumann had published two major mathematical papers, the second of which gave the modern definition of ordinal numbers, which superseded Georg Cantor's definition. At the conclusion of his education at the gymnasium, von Neumann sat for and won the Eötvös Prize, a national prize for mathematics. University studies. According to his friend Theodor von Karman, von Neumann's father wanted John to follow him into industry and thereby invest his time in a more financially useful endeavor than mathematics. In fact, his father requested Theodor von Karman to persuade his son not to take mathematics as his major. Von Neumann and his father decided that the best career path was to become a chemical engineer. This was not something that von Neumann had much knowledge of, so it was arranged for him to take a 2-year, non-degree course in chemistry at the University of Berlin, after which he sat for the entrance exam to the prestigious ETH Zurich, which he passed in September 1923. At the same time, von Neumann also entered Pázmány Péter University in Budapest, as a PhD candidate in mathematics. For his thesis, he chose to produce an axiomatization of Cantor's set theory. He graduated as a chemical engineer from ETH Zurich in 1926, although Wigner says that von Neumann was never very attached to the subject of chemistry, and passed his final examinations for his PhD in mathematics simultaneously with his chemical engineering degree, of which Wigner wrote, "Evidently a PhD thesis and examination did not constitute an appreciable effort." He then went to the University of Göttingen on a grant from the Rockefeller Foundation to study mathematics under David Hilbert. Early career and private life. Von Neumann's habilitation was completed on December 13, 1927. And he started his lectures as a private dozen at the University of Berlin in 1928, being the youngest person ever elected private dozen in the university's history in any subject. By the end of 1927, von Neumann had published 12 major papers in mathematics, and by the end of 1929, 32 papers, at a rate of nearly one major paper per month. His reputed powers of memorization and recall allowed him to quickly memorize the pages of telephone directories, and recite the names, addresses and numbers therein. In 1929, he briefly became a private dozen at the University of Hamburg, where the prospects of becoming a tenured professor were better, but in October of that year a better offer presented itself when he was invited to Princeton University in Princeton, New Jersey. On New Year's Day in 1930, von Neumann married Marietta Kovesi, who had studied economics at Budapest University. Von Neumann and Marietta had one child, a daughter, Marina, born in 1935. As of 2017, she is a distinguished professor of business administration and public policy at the University of Michigan. The couple divorced in 1937. In October 1938, von Neumann married Clara Dan, whom he had met during his last trips back to Budapest prior to the outbreak of World War II. Prior to his marriage to Marietta, von Neumann was baptized a Catholic in 1930. Von Neumann's father, Max, had died in 1929. None of the family had converted to Christianity while Max was alive, but all did afterward. In 1933, he was offered a lifetime professorship on the faculty of the Institute for Advanced Study in New Jersey when that institution's plan to appoint Hermann Weyl fell through. He remained a mathematics professor there until his death, although he had announced his intention to resign and become a professor at large at the University of California, Los Angeles. His mother, brothers and in-laws followed von Neumann to the United States in 1939. Von Neumann anglicized his first name to John, keeping the German aristocratic surname of von Neumann. His brothers changed theirs to Neumann and von Neumann. Von Neumann became a naturalized citizen of the United States in 1937, and immediately tried to become a lieutenant in the United States Army's Officers Reserve Corps. He passed the exams easily, but was ultimately rejected because of his age. His pre-war analysis of how France would stand up to Germany is often quoted, "Oh, France won't matter." Clara and John von Neumann were socially active within the local academic community. His white clapboard house at 26 Westcott Road was one of the largest private residences in Princeton. He took great care of his clothing and would always wear formal suits. He once wore a three-piece pinstripe when he rode down the Grand Canyon astride a mule. Hilbert is reported to have asked Prey, who is the candidate's tailor, at von Neumann's 1926 doctoral exam, as he had never seen such beautiful evening clothes. Von Neumann held a lifelong passion for ancient history, being renowned for his prodigious historical knowledge. A professor of Byzantine history at Princeton once said that von Neumann had greater expertise in Byzantine history than he did. Von Neumann liked to eat and drink. His wife, Clara, said that he could count everything except calories. He enjoyed Yiddish and off-color humor, especially limericks. He was a non-smoker. In Princeton, he received complaints for regularly playing extremely loud German march music on his gramophone, which distracted those in neighboring offices, including Albert Einstein, from their work. Von Neumann did some of his best work in noisy, chaotic environments, and once admonished his wife for preparing a quiet study for him to work in. He never used it, preferring the couple's living room with its television playing loudly. Despite being a notoriously bad driver, he nonetheless enjoyed driving, frequently while reading a book, occasioning numerous arrests as well as accidents. When Cuthbert Hurd hired him as a consultant to IBM, Hurd often quietly paid the fines for his traffic tickets. Von Neumann's closest friend in the United States was mathematician Stanislaw Ulam. A later friend of Ulam's, Giancarlo Rota, wrote, "They would spend hours on end gossiping and giggling, swapping Jewish jokes, and drifting in and out of mathematical talk." When von Neumann was dying in the hospital, every time Ulam visited, he came prepared with a new collection of jokes to cheer him up. He believed that much of his mathematical thought occurred intuitively, and he would often go to sleep with a problem unsolved and know the answer immediately upon waking up. Ulam noted that von Neumann's way of thinking might not be visual, but more oral. Mathematics. Set theory. The axiomatization of mathematics, on the model of Euclid's Elements, had reached new levels of rigor and breadth at the end of the 19th century, particularly in arithmetic, thanks to the axiom scheme of Richard Dedekind and Charles Sanders Peirce, and in geometry, thanks to Hilbert's axioms. But at the beginning of the 20th century, efforts to base mathematics on naive set theory suffered a setback due to Russell's paradox, on the set of all sets that do not belong to themselves. The problem of an adequate axiomatization of set theory was resolved implicitly about 20 years later by Ernst Zermelo and Abraham Fraenkel. Zermelo-Fraenkel set theory provided a series of principles that allowed for the construction of the sets used in the everyday practice of mathematics, but they did not explicitly exclude the possibility of the existence of a set that belongs to itself. In his doctoral thesis of 1925, von Neumann demonstrated two techniques to exclude such sets, the axiom of foundation and the notion of class. The axiom of foundation proposed that every set can be constructed from the bottom up in an ordered succession of steps by way of the principles of Zermelo and Fraenkel. If one set belongs to another, then the first must necessarily come before the second in the succession. This excludes the possibility of a set belonging to itself. To demonstrate that the addition of this new axiom to the others did not produce contradictions, von Neumann introduced a method of demonstration, called the method of intermodels, which later became an essential instrument in set theory. The second approach to the problem of sets belonging to themselves took as its base the notion of class, and defines a set as a class which belongs to other classes, while a proper class is defined as a class which does not belong to other classes. Under the Zermelo-Fraenkel approach, the axioms impede the construction of a set of all sets which do not belong to themselves. In contrast, under the von Neumann approach, the class of all sets which do not belong to themselves can be constructed. but it is a proper class and not a set. With this contribution of von Neumann, the axiomatic system of the theory of sets avoided the contradictions of earlier systems, and became usable as a foundation for mathematics, despite the lack of a proof of its consistency. The next question was whether it provided definitive answers to all mathematical questions that could be posed in it, or whether it might be improved by adding stronger axioms that could be used to prove a broader class of theorems. A strongly negative answer to whether it was definitive arrived in September 1930 at the historic Mathematical Congress of Königsberg, in which Kurt Gödel announced his first theorem of incompleteness. The usual axiomatic systems are incomplete, in the sense that they cannot prove every truth which is expressible in their language. Moreover, every consistent extension of these systems would necessarily remain incomplete. Less than a month later, von Neumann, who had participated at the Congress, communicated to Gödel an interesting consequence of his theorem, that the usual axiomatic systems are unable to demonstrate their own consistency. However, Gödel had already discovered this consequence, now known as his second incompleteness theorem, and he sent von Neumann a preprint of his article containing both incompleteness theorems. Von Neumann acknowledged Gödel's priority in his next letter. He never thought much of the American system of claiming personal priority for everything. Von Neumann paradox. Building on the work of Felix Hausdorff, in 1924 Stefan Banach and Alfred Tarski proved that given a solid ball in three-dimensional space, there exists a decomposition of the ball into a finite number of disjoint subsets, that can be reassembled together in a different way to yield two identical copies of the original ball. Banach and Tarski proved that, using isometric transformations, the result of taking the apart and reassembling a two-dimensional figure would necessarily have the same area as the original. This would make creating two unit squares out of one impossible. However, in a 1929 paper, von Neumann proved that paradoxical decompositions could use a group of transformations that include as a subgroup a free group with two generators. The group of area-preserving transformations contains such subgroups, and this opens the possibility of performing paradoxical decompositions using these subgroups. The class of groups isolated by von Neumann in his work on Banach-Tarski decompositions subsequently was very important for many areas of mathematics, including von Neumann's own later work in measure theory, see below. Ergodic theory. In a series of famous papers that were published in 1932, von Neumann made foundational contributions to ergodic theory, a branch of mathematics that involves the states of dynamical systems with an invariant measure. Of the 1932 papers on ergodic theory, Paul Holmes writes that even if von Neumann had never done anything else, they would have been sufficient to guarantee him mathematical immortality. By then von Neumann had already written his famous articles on operator theory, and the application of this work was instrumental in the von Neumann mean ergodic theorem. Operator theory. Von Neumann introduced the study of rings of operators, through the von Neumann algebras. A von Neumann algebra is an algebra of bounded operators on a Hilbert space that is closed in the weak operator topology and contains the identity operator. The von Neumann bicommutant theorem shows that the analytic definition is equivalent to a purely algebraic definition as being equal to the bicommutant. Von Neumann embarked in 1936, with the partial collaboration of F. J. Murray, on the general study of factors classification of von Neumann algebras. The 6 major papers in which he developed the theory between 1936 and 1940 rank among the masterpieces of analysis in the 20th century. The direct integral was later introduced in 1949 by John von Neumann. Measure theory. In measure theory, the problem of measure for an n-dimensional Euclidean space Rn may be stated as, does there exist a positive, normalized, invariant, and additive set function on the class of all subsets of Rn? The work of Felix Hausdorff and Stefan Banach had implied that the problem of measure has a positive solution if n equals 1 or n equals 2 and a negative solution, because of the Banach-Tarski paradox, in all other cases. Von Neumann's work argued that the problem is essentially group-theoretic in character. The existence of a measure could be determined by looking at the properties of the transformation group of the given space. The positive solution for spaces of dimension at most 2, and the negative solution for higher dimensions, comes from the fact that the Euclidean group is a solvable group for dimension at most 2, and is not solvable for higher dimensions. Thus, according to von Neumann, it is the change of group that makes a difference, not the change of space. In a number of von Neumann's papers, the methods of argument he employed are considered even more significant than the results. In anticipation of his later study of dimension theory and algebras of operators, von Neumann used results on equivalence by finite decomposition, and reformulated the problem of measure in terms of functions. In his 1936 paper on analytic measure theory, he used the Haar theorem in the solution of Hilbert's fifth problem in the case of compact groups. In 1938, he He was awarded the Bacher Memorial Prize for his work in analysis. Geometry. Von Neumann founded the field of continuous geometry. It followed his path-breaking work on rings of operators. In mathematics, continuous geometry is a substitute of complex projective geometry, where instead of the dimension of a subspace being in a discrete set 0, 1, n, it can be an element of the unit interval. Earlier, Menger and Birkhoff had axiomatized complex projective geometry in terms of the properties of its lattice of linear subspaces. Von Neumann, following his work on rings of operators, weakened those axioms to describe a broader class of lattices, the continuous geometries. While the dimensions of the subspaces of projective geometries are a discrete set, the non-negative integers, the dimensions of the elements of a continuous geometry can range continuously across the unit interval. Von Neumann was motivated by his discovery of von Neumann algebras with a dimension function taking a continuous range of dimensions, and the first example of a continuous geometry other than projective space was the projections of the hyperfinite type 2 factor. Lattice theory. Between 1937 and 1939, von Neumann worked on lattice theory, the theory of partially ordered sets in which every two elements have a greatest lower bound and a least upper bound. Garrett Birkhoff writes, John von Neumann's brilliant mind blazed over lattice theory like a meteor. Von Neumann provided an abstract exploration of dimension and completed complemented modular topological lattices, properties that arise in the lattices of subspaces of inner product spaces. Dimension is determined, up to a positive linear transformation, by the following two properties. It is conserved by perspective mappings, perspectivities, and ordered by inclusion. The deepest part of the proof concerns the equivalence of perspectivity with projectivity by decomposition of which a corollary is the transitivity of perspectivity. Additionally, in the general case, von Neumann proved the following basic representation theorem. Any complemented modular lattice L having a basis of n greater than or equal to 4 pairwise perspective elements, is isomorphic with the lattice RR of all principal right ideals of a suitable regular ring R. This conclusion is the culmination of 140 pages of brilliant and incisive algebra involving entirely novel axioms. Anyone wishing to get an unforgettable impression of the razor edge of von Neumann's mind, need merely try to pursue this chain of exact reasoning for himself, realizing that often 5 pages of it were written down before breakfast, seated at a living room writing table in a bathrobe. Mathematical formulation of quantum mechanics. Von Neumann was the first to establish a rigorous mathematical framework for quantum mechanics, known as the Dirac-von Neumann axioms, with his 1932 work Mathematical Foundations of Quantum Mechanics. After having completed the axiomatization of set theory, he began to confront the axiomatization of quantum mechanics. He realized, in 1926, that a state of a quantum system could be represented by a point in a complex Hilbert space that, in general, could be infinite dimensional even for a single particle. In this formalism of quantum mechanics, observable quantities such as position or momentum are represented as linear operators acting on the Hilbert space associated with the quantum system. The physics of quantum mechanics was thereby reduced to the mathematics of Hilbert spaces and linear operators acting on them. For example, the uncertainty principle, according to which the determination of the position of a particle prevents the determination of its momentum and vice versa, is translated into the non-commutativity of the two corresponding operators. This new mathematical formulation included as special cases the formulations of both Heisenberg and Schrödinger. When Heisenberg was informed von Neumann had clarified the difference between an unbounded operator that was a self-adjoint operator and one that was merely symmetric, Heisenberg replied, what is the difference? Von Neumann's abstract treatment permitted him also to confront the foundational issue of determinism versus non-determinism, and in the book he presented a proof that the statistical results of quantum mechanics could not possibly be averages of an underlying set of determined hidden variables, as in classical statistical mechanics. In 1935, Greta Hermann published a paper arguing that the proof contained a conceptual error and was therefore invalid. Hermann's work was largely ignored until after John S. Bell made essentially the same argument in 1966. However, in 2010, Jeffrey Bubb argued that Bell had misconstrued von Neumann's proof, and pointed out that the proof, though not valid for all hidden variable theories, does rule out a well-defined and important subset. Bubb also suggests that von Neumann was aware of this limitation, and that von Neumann did not claim that his proof completely ruled out hidden variable theories. The validity of Bubb's argument is, in turn, disputed. In any case, Gleason's theorem of 1957 fills the gaps in von Neumann's approach. Von Neumann's proof inaugurated a line of research that ultimately led, through the work of Bell in 1964 on Bell's theorem, and the experiments of Alain Aspect in 1982, to the demonstration that quantum physics either requires a notion of reality substantially different from that of classical physics, or must include non-locality and apparent violation of special relativity. In a chapter of the Mathematical Foundations of Quantum Mechanics, von Neumann deeply analyzed the so-called measurement problem. He concluded that the entire physical universe could be made subject to the universal wave function. Since something outside the calculation was needed to collapse the wave function, von Neumann concluded that the collapse was caused by the consciousness of the experimenter. Von Neumann argued that the mathematics of quantum mechanics allows the collapse of the wave function to be placed at any position in the causal chain from the measurement device to the subjective consciousness of the human observer. Although this view was accepted by Eugen Wigner, the von Neumann-Wigner interpretation never gained acceptance amongst the majority of physicists. The von Neumann-Wigner interpretation has been summarized as follows. Though theories of quantum mechanics continue to evolve to this day, there is a basic framework for the mathematical formalism of problems in quantum mechanics which underlies the majority of approaches and can be traced back to the mathematical formalisms and techniques first used by von Neumann. In other words, discussions about interpretation of the theory, and extensions to it, are now mostly conducted on the basis of shared assumptions about the mathematical foundations. Von Neumann entropy. Von Neumann entropy is extensively used in different forms, conditional entropies, relative entropies, etc., in the framework of quantum information theory. Entanglement measures are based upon some quantity directly related to the von Neumann entropy. Given a statistical ensemble of quantum mechanical systems with the density matrix ρ, \displaystyle\ρ, it is given by S, ρ, equals minus dr, ρ in ρ. \displaystyle S \rho equals \operator name, dr, \rho lane \rho. Many of the same entropy measures in classical information theory can also be generalized to the quantum case, such as Holvo entropy and the conditional quantum entropy. Quantum mutual information. Quantum information theory is largely concerned with the interpretation and uses of von Neumann entropy. The von Neumann entropy is the cornerstone in the development of quantum information theory, while the Shannon entropy applies to classical information theory. This is considered a historical anomaly, as it might have been expected that Shannon entropy was discovered prior to von Neumann entropy, given the latter's more widespread application to quantum information theory. However, the historical reverse occurred. Von Neumann first discovered von Neumann entropy, and applied it to questions of statistical physics. Decades later, Shannon developed an information theoretic formula for use in classical information theory, and asked von Neumann what to call it, with von Neumann telling him to call it Shannon entropy, as it was a special case of von Neumann entropy. Density matrix. The formalism of density operators and matrices was introduced by von Neumann in 1927 and independently, but less systematically by Lev Landau and Felix Bloch in 1927 and 1946 respectively. The density matrix is an alternative way in which to represent the state of a quantum system, which could otherwise be represented using the wave function. The density matrix allows the solution of certain time-dependent problems in quantum mechanics. Von Neumann measurement scheme. The von Neumann measurement scheme, the ancestor of quantum decoherence theory, represents measurements projectively by taking into account the measuring apparatus which is also treated as a quantum object. The projective measurement scheme introduced by von Neumann led to the development of quantum decoherence theories. Quantum logic. Von Neumann first proposed a quantum logic in his 1932 treatise Mathematical Foundations of Quantum Mechanics, where he noted that projections on a Hilbert space can be viewed as propositions about physical observables. The field of quantum logic was subsequently inaugurated, in a famous paper of 1936 by von Neumann and Gerrit Birkhoff, the first work ever to introduce quantum logics, wherein von Neumann and Birkhoff first proved that quantum mechanics requires a propositional calculus substantially different from all classical logics and rigorously isolated a new algebraic structure for quantum logics. The concept of creating a propositional calculus for quantum logic was first outlined in a short section in von Neumann's 1932 work, but in 1936, the need for the new propositional calculus was demonstrated through several proofs. For example, photons cannot pass through two successive filters that are polarized perpendicularly, for example, one horizontally and the other vertically, and therefore, a fortiori, it cannot pass if a third filter polarized diagonally is added to the other two, either before or after them in the succession. But if the third filter is added in between the other two, the photons will, indeed, pass through. This experimental fact is translatable into logic as the non-commutativity of conjunction, a B, does not equal, BA, \displaystyle, A/land B/nec, B/land A. It was also demonstrated that the laws of distribution of classical logic, P, QR, equals, PQ, PR, \displaystyle P\lor, Q\land R equals P\lor Q\land, P\lor R, and P, QR, equals, PQ, PR, \displaystyle P\land, Q\lor R equals P\land Q\lor, P\land R, are not valid for quantum theory. The reason for this is that a quantum disjunction, unlike the case for classical disjunction, can be true even when both of the disjuncts are false, and this is, in turn, attributable to the fact that it is frequently the case, in quantum mechanics, that a pair of alternatives are semantically determinate, while each of its members are necessarily indeterminate. This latter property can be illustrated by a simple example. Suppose we are dealing with particles, such as electrons, of semi-integral spin angular momentum, for which there are only two possible values, positive or negative. Then, a principle of indetermination establishes that the spin, relative to two different directions, for example, x and y, results in a pair of incompatible quantities. Suppose that the state of a certain electron verifies the proposition the spin of the electron in the x direction is positive. By the principle of indeterminacy, the value of the spin in the direction y will be completely indeterminate for. Hence, can verify neither the proposition the spin in the direction of y is positive nor the proposition the spin in the direction of y is negative. Nevertheless, the disjunction of the propositions the spin in the direction of y is positive or the spin in the direction of y is negative must be true for. In the case of distribution, it is therefore possible to have a situation in which a, b, c, equals a 1 equals a, \displaystyle a\land, b\lor c equals a\land 1 equals a, while, a b, a c, equals 0 equals 0, \displaystyle a\land b\lor, a\land c equals 0 \lor 0 equals 0. As Hilary Putnam writes, von Neumann replaced classical logic with a logic constructed in orthomodular lattices, isomorphic to the lattice of subspaces of the Hilbert space of a given physical system. Game theory. Von Neumann founded the field of game theory as a mathematical discipline. Von Neumann proved his minimax theorem in 1928. This theorem establishes that in zero-sum games with perfect information, i.e. in which players know at each time all moves that have taken place so far, there exists a pair of strategies for both players that allows each to minimize his maximum losses, hence the name minimax. When examining every possible strategy, a player must consider all the possible responses of his adversary. The player then plays out the strategy that will result in the minimization of his maximum loss. Such strategies, which minimize the maximum loss for each player, are called optimal. Von Neumann showed that their minimaxes are equal, in absolute value, and contrary, in sign. Von Neumann improved and extended the minimax theorem to include games involving imperfect information and games with more than two players, publishing this result in his 1944 Theory of Games and Economic Behavior, written with Oscar Morgenstern. Morgenstern wrote a paper on game theory and thought he would show it to von Neumann because of his interest in the subject. He read it and said to Morgenstern that he should put more in it. This was repeated a couple of times, and then von Neumann became a co-author and the paper became 100 pages long. Then it became a book. The public interest in this work was such that the New York Times ran a front-page story. In this book, von Neumann declared that economic theory needed to use functional analytic methods, especially convex sets and topological fixed-point theorem, rather than the traditional differential calculus, because the maximum operator did not preserve differentiable functions. Independently, Leonid Kontorovich's functional analytic work on mathematical economics also focused attention on optimization theory, non-differentiability, and vector lattices. Von Neumann's functional analytic techniques, the use of duality pairings of real vector spaces to represent prices and quantities, the use of supporting and separating hyperplanes and convex sets, and fixed-point theory, have been the primary tools of mathematical economics ever since. Mathematical economics. Von Neumann raised the intellectual and mathematical level of economics in several influential publications. For his model of an expanding economy, von Neumann proved the existence and uniqueness of an equilibrium using his generalization of the Brouwer fixed-point theorem. Von Neumann's model of an expanding economy considered the matrix pencil A minus lambda B with non-negative matrices A and B. Von Neumann sought probability vectors P and Q and a positive number lambda that would solve the complementarity equation, along with two inequality systems expressing economic efficiency. In this model, The transposed probability vector P represents the prices of the goods, while the probability vector Q represents the intensity at which the production process would run. The unique solution lambda represents the growth factor, which is 1 plus the rate of growth of the economy. The rate of growth equals the interest rate. Von Neumann's results have been viewed as a special case of linear programming, where von Neumann's model uses only non-negative matrices. The study of von Neumann's model of an expanding economy continues to interest mathematical economists with interests in computational economics. This paper has been called the greatest paper in mathematical economics by several authors, who recognized its introduction of fixed-point theorems, linear inequalities, complementary slackness, and saddle-point duality. In the proceedings of a conference on von Neumann's growth model, Paul Samuelson said that many mathematicians had developed methods useful to economists, but that von Neumann was unique in having made significant contributions to economic theory itself. Von Neumann's famous 9-page paper started life as a talk at Princeton and then became a paper in German, which was eventually translated into English. His interest in economics that led to that paper began as follows. When lecturing at Berlin in 1928 and 1929, he spent his summers back home in Budapest, and so did the economist Nicholas Kaldor, and they hit it off. Kaldor recommended that von Neumann read a book by the mathematical economist Leon Walras. Von Neumann found some faults in that book and corrected them, for example, replacing equations by inequalities. He noticed that Walras' general equilibrium theory and Walras law, which led to systems of simultaneous linear equations, could produce the absurd result that the profit could be maximized by producing and selling a negative quantity of a product. He replaced the equations by inequalities, introduced dynamic equilibria, among other things, and eventually produced the paper Linear Programming. Building on his results on matrix games and on his model of an expanding economy, von Neumann invented the theory of duality in linear programming when George Dantzig described his work in a few minutes, and an impatient von Neumann asked him to get to the point. Then, Dantzig listened dumbfounded while von Neumann provided an hour lecture on convex sets, fixed-point theory, and duality, conjecturing the equivalence between matrix games and linear programming. Later, von Neumann suggested a new method of linear programming, using the homogeneous linear system of Paul Gordon, 1873, which was later popularized by Karmarkar's algorithm. Von Neumann's method used a pivoting algorithm between simplices, with the pivoting decision determined by a non-negative least squares subproblem with a convexity constrained, projecting the zero vector onto the convex hull of the active simplex. Von Neumann's algorithm was the first interior point method of linear programming. Mathematical statistics. Von Neumann made fundamental contributions to mathematical statistics. In 1941, he derived the exact distribution of the ratio of the mean square of successive differences to the sample variance for independent and identically normally distributed variables. This ratio was applied to the residuals from regression models and is commonly known as the Durbin-Watson statistic for testing the null hypothesis that the errors are serially independent against the alternative that they follow a stationary first-order autoregression. Subsequently, Denis Sargan and Alok Bhargava extended the results for testing if the errors on a regression model follow a Gaussian random walk, i.e., possess a unit root, against the alternative that they are a stationary first-order autoregression. Fluid dynamics. Von Neumann made fundamental contributions in the field of fluid dynamics. Von Neumann's contributions to fluid dynamics included his discovery of the classic flow solution to blast waves, and the co-discovery, independently of Yakov Borisovich Zeldovich and Werner Düring, of the ZND detonation model of explosives. During the 1930s, von Neumann became an authority on the mathematics of shaped charges. Later, with Robert D. Richtmeier, von Neumann developed an algorithm defining artificial viscosity that improved the understanding of shock waves. When computers solved hydrodynamic or aerodynamic problems, they tried to put too many computational grid points at regions of sharp discontinuity, shock waves. The mathematics of artificial viscosity smoothed the shock transition without sacrificing basic physics. Von Neumann soon applied computer modeling to the field, developing software for his ballistics research. During World War II, he arrived one day at the office of R. H. Kent, the director of the U.S. Army's Ballistic Research Laboratory, with a computer program he had created for calculating a one-dimensional model of 100 molecules to simulate a shock wave. Von Neumann then gave a seminar on his computer program to an audience which included his friend Theodore von Karman. After von Neumann had finished, von Karman said, "Well, Johnny, that's very interesting. Of course you realize Lagrange also used digital models to simulate continuum mechanics." It was evident from von Neumann's face that he had been unaware of Lagrange's mécanique analytique. Mastery of mathematics. Stanley Lamb, who knew von Neumann well, described his mastery of mathematics this way: most mathematicians know one method. For example, Norbert Wiener had mastered Fourier transforms. Some mathematicians have mastered two methods and might really impress someone who knows only one of them. John von Neumann had mastered three methods. He went on to explain that the three methods were: Edward Teller wrote that nobody knows all science, not even von Neumann did. But as for mathematics, he contributed to every part of it except number theory and topology. That is, I think, something unique. Von Neumann was asked to write an essay for the layman describing what mathematics is, and produced a beautiful analysis. He explained that mathematics straddles the world between the empirical and logical, arguing that geometry was originally empirical, but Euclid constructed a logical, deductive theory. However, he argued that there is always the danger of straying too far from the real world and becoming irrelevant sophistry. Nuclear weapons. Manhattan Project. Beginning in the late 1930s, von Neumann developed an expertise in explosions, phenomena that are difficult to model mathematically. During this period, von Neumann was the leading authority of the mathematics of shaped charges. This led him to a large number of military consultancies, primarily for the Navy, which in turn led to his involvement in the Manhattan Project. The involvement included frequent trips by train to the project's secret research facilities at the Los Alamos laboratory in a remote part of New Mexico. Von Neumann made his principal contribution to the atomic bomb in the concept and design of the explosive lenses that were needed to compress the plutonium core of the Fat Man weapon that was later dropped on Nagasaki. While von Neumann did not originate the implosion concept, he was one of its most persistent proponents, encouraging its continued development against the instincts of many of his colleagues, who felt such a design to be unworkable. He also eventually came up with the idea of using more powerful shaped charges and less fissionable material to greatly increase the speed of assembly. When it turned out that there would not be enough uranium-235 to make more than one bomb, the implosive lens project was greatly expanded and von Neumann's idea was implemented. Implosion was the only method that could be used with the plutonium-239 that was available from the Hanford site. He established the design of the explosive lens as required, but there remained concerns about edge effects and imperfections in the explosives. His calculations showed that implosion would work if it did not depart by more than 5% from spherical symmetry. After a series of failed attempts with models, this was achieved by George Kistiakowsky, and the construction of the Trinity bomb was completed in July 1945. In a visit to Los Alamos in September 1944, von Neumann showed that the pressure increase from explosion shock wave reflection from solid objects was greater than previously believed if the angle of incidence of the shock wave was between 90 degrees and some limiting angle. As a result, it was determined that the effectiveness of an atomic bomb would be enhanced with detonation some kilometers above the target, rather than at ground level. Von Neumann, 4 other scientists, and various military personnel were included in the target selection committee that was responsible for choosing the Japanese cities of Hiroshima and Nagasaki as the first targets of the atomic bomb. Von Neumann oversaw computations related to the expected size of the bomb blasts, estimated death tolls, and the distance above the ground at which the bombs should be detonated for optimum shockwave propagation and thus maximum effect. The cultural capital Kyoto, which had been spared the bombing inflicted upon militarily significant cities, was von Neumann's first choice, a selection seconded by Manhattan Project leader General Leslie Groves. However, this target was dismissed by Secretary of War Henry L. Stimson. On July 16, 1945, von Neumann and numerous other Manhattan Project personnel were eyewitnesses to the first test of an atomic bomb detonation, which was codenamed Trinity. The event was conducted as a test of the implosion method device, at the bombing range near Alamogordo Army Airfield, 35 miles, 56 kilometers, southeast of Socorro, New Mexico. Based on his observation alone, von Neumann estimated the test had resulted in a blast equivalent to 5 kilotons of TNT, 21 TJ. But Enrico Fermi produced a more accurate estimate of 10 kilotons by dropping scraps of torn-up paper as the shock wave passed his location and watching how far they scattered. The actual power of the explosion had been between 20 and 22 kilotons. It was in von Neumann's 1944 papers that the expression kilotons appeared for the first time. After the war, Robert Oppenheimer remarked that the physicists involved in the Manhattan Project had known sin. Von Neumann's response was that sometimes someone confesses a sin in order to take credit for it. Von Neumann continued unperturbed in his work and became, along with Edward Teller, one of those who sustained the hydrogen bomb project. He collaborated with Klaus Fuchs on further development of the bomb, and in 1946 the two filed a secret patent on improvement in methods and means for utilizing nuclear energy, which outlined a scheme for using a fission bomb to compress fusion fuel to initiate nuclear fusion. The Fuchs-von Neumann patent used radiation implosion, but not in the same way as is used in what became the final hydrogen bomb design, the Teller-Ulam design. Their work was, however, incorporated into the George shot of Operation Greenhouse, which was instructive in testing out concepts that went into the final design. The Fuchs-von Neumann work was passed on to the Soviet Union by Fuchs as part of his nuclear espionage, but it was not used in the Soviets' own, independent development of the Teller-Ulam design. The historian Jeremy Bernstein has pointed out that ironically, John von Neumann and Klaus Fuchs produced a brilliant invention in 1946 that could have changed the whole course of the development of the hydrogen bomb, but was not fully understood until after the bomb had been successfully made. For his wartime services, von Neumann was awarded the Navy Distinguished Civilian Service Award in July 1946, and the Medal for Merit in October 1946. Atomic Energy Commission. In 1950, von Neumann became a consultant to the Weapons Systems Evaluation Group, WSEG, whose function was to advise the Joint Chiefs of Staff and the United States Secretary of Defense on the development and use of new technologies. He also became an advisor to the Armed Forces Special Weapons Project, AFSP, which was responsible for the military aspects on nuclear weapons. Over the following 2 years, he became a consultant to the Central Intelligence Agency, CIA, a member of the influential General Advisory Committee of the Atomic Energy Commission, a consultant to the newly established Lawrence Livermore National Laboratory, and a member of the Scientific Advisory Group of the United States Air Force. In 1955, von Neumann became a commissioner of the AEC. He accepted this position and used it to further the production of compact hydrogen bombs suitable for intercontinental ballistic missile delivery. He involved himself in correcting the severe shortage of tritium and lithium-6 needed for these compact weapons, and he argued against settling for the intermediate-range missiles that the Army wanted. He was adamant that H-bombs delivered into the heart of enemy territory by an ICBM would be the most effective weapon possible, and that the relative inaccuracy of the missile wouldn't be a problem with an H-bomb. He said the Russians would probably be building a similar weapon system, which turned out to be the case. Despite his disagreement with Oppenheimer over the need for a crash program to develop the hydrogen bomb, he testified on the latter's behalf at the 1954 Oppenheimer security hearing, at which he asserted that Oppenheimer was loyal, and praised him for his helpfulness once the program went ahead. Shortly before his death from cancer, von Neumann headed the United States government's top-secret ICBM committee, which would sometimes meet in his home. Its purpose was to decide on the feasibility of building an ICBM large enough to carry a thermonuclear weapon. Von Neumann had long argued that while the technical obstacles were sizable, they could be overcome in time. The SM-65 Atlas passed its first fully functional test in 1959, 2 years after his death. The feasibility of an ICBM owed as much to improved, smaller warheads as it did to developments in rocketry, and his understanding of the former made his advice invaluable. Mutual assured destruction. Von Neumann is credited with developing the equilibrium strategy of mutual assured destruction, MAD. He also moved heaven and earth to bring MAD about. His goal was to quickly develop ICBMs and the compact hydrogen bombs that they could deliver to the USSR, and he knew the Soviets were doing similar work because the CIA interviewed German rocket scientists who were allowed to return to Germany, and von Neumann had planted a dozen technical people in the CIA. The Soviets considered that bombers would soon be vulnerable, and they shared von Neumann's view that an H-bomb in an ICBM was the ne plus ultra of weapons. They believed that whoever had superiority in these weapons would take over the world, without necessarily using them. He was afraid of a missile gap and took several more steps to achieve his goal of keeping up with the Soviets. Von Neumann's assessment that the Soviets had a lead in missile technology, considered pessimistic at the time, was soon proven correct in the Sputnik crisis. Von Neumann entered government service primarily because he felt that, if freedom and civilization were to survive, it would have to be because the United States would triumph over totalitarianism from Nazism, fascism, and Soviet communism. During a Senate committee hearing he described his political ideology as violently anti-communist, and much more militaristic than the norm. He was quoted in 1950 remarking, "If you say why not bomb tomorrow, I say, why not today? If you say today at 5 o'clock, I say why not 1 o'clock?" On February 15, 1956, von Neumann was presented with the Medal of Freedom by President Dwight D. Eisenhower. His citation read, "Computing. Von Neumann was a founding figure in computing. Von Neumann was the inventor, in 1945, of the merge sort algorithm, in which the first and second halves of an array are each sorted recursively and then merged. Von Neumann wrote the 23 pages long sorting program for the Edvots in ink. On the first page, traces of the phrase "top secret," which was written in pencil and later erased, can still be seen. He also worked on the philosophy of artificial intelligence with Alan Turing when the latter visited Princeton in the 1930s. Von Neumann's hydrogen bomb work was played out in the realm of computing, where he and Stanislaw Ulam developed simulations on von Neumann's digital computers for the hydrodynamic computations. During this time he contributed to the development of the Monte Carlo method, which allowed solutions to complicated problems to be approximated using random numbers. Von Neumann's algorithm for simulating a fair coin with a biased coin is used in the software whitening stage of some hardware random number generators. Because using lists of truly random numbers was extremely slow, von Neumann developed a form of making pseudorandom numbers, using the middle square method. Though this method has been criticized as crude, von Neumann was aware of this. He justified it as being faster than any other method at his disposal, writing that anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. Von Neumann also noted that when this method went awry it did so obviously, unlike other methods which could be subtly incorrect. While consulting for the Moore School of Electrical Engineering at the University of Pennsylvania on the Edvots project, von Neumann wrote an incomplete first draft of a report on the Edvots. The paper, whose premature distribution nullified the patent claims of Edvots designers J. Presper Eckert and John Mauchly, described a computer architecture in which the data and the program are both stored in the computer's memory in the same address space. This architecture is the basis of most modern computer designs, unlike the earliest computers that were programmed using a separate memory device such as a paper tape or plugboard. Although the single memory, stored program architecture is commonly called von Neumann architecture as a result of von Neumann's paper, the architecture was based on the work of Eckert and Mauchly, inventors of the ENIAC computer at the University of Pennsylvania. John von Neumann consulted for the Army's Ballistic Research Laboratory, most notably on the ENIAC project, as a member of its Scientific Advisory Committee. The electronics of the new ENIAC ran at 1/6 the speed, but this in no way degraded the ENIAC's performance, since it was still entirely I/O-bound. Complicated programs could be developed and debugged in days rather than the weeks required for plugboarding the old ENIAC. Some of von Neumann's early computer programs have been preserved. The next computer that von Neumann designed was the EAS machine at the Institute for Advanced Study in Princeton, New Jersey. He arranged its financing, and the components were designed and built at the RCA Research Laboratory nearby. John von Neumann recommended that the IBM 701, nicknamed the defense computer, include a magnetic drum. It was a faster version of the EAS machine and formed the basis for the commercially successful IBM 704. Stochastic computing was first introduced in a pioneering paper by von Neumann in 1953. However, the theory could not be implemented until advances in computing of the 1960s. Cellular automata, DNA and the universal constructor. Von Neumann's rigorous mathematical analysis of the structure of self-replication, of the semiotic relationship between constructor, description and that which is constructed, preceded the discovery of the structure of DNA. Von Neumann created the field of cellular automata without the aid of computers, constructing the first self-replicating automata with pencil and graph paper. The detailed proposal for a physical non-biological self-replicating system was first put forward in lectures von Neumann delivered in 1948 and 1949, when he first only proposed a kinematic self-reproducing automaton. While qualitatively sound, von Neumann was evidently dissatisfied with this model of a self-replicator due to the difficulty of analyzing it with mathematical rigor. He went on to instead develop a more abstract model self-replicator based on his original concept of cellular automata. Subsequently, the concept of the von Neumann universal constructor based on the von Neumann cellular automaton was fleshed out in his posthumously published lectures Theory of Self-Reproducing Automata. Ulam and von Neumann created a method for calculating liquid motion in the 1950s. The driving concept of the method was to consider a liquid as a group of discrete units and calculate the motion of each based on its neighbor's behaviors. Like Ulam's lattice network, von Neumann's cellular automata are two-dimensional, with his self-replicator implemented algorithmically. The result was a universal copier and constructor working within a cellular automaton with a small neighborhood, only those cells that touch are neighbors, for von Neumann's cellular automata, only orthogonal cells, and with 29 states per cell. Von Neumann gave an existence proof that a particular pattern would make infinite copies of itself within the given cellular universe by designing a 200,000 cell configuration that could do so. Von Neumann addressed the evolutionary growth of complexity amongst his self-replicating machines. His proof of principle design showed how it is logically possible, by using a general-purpose programmable, universal, constructor, to exhibit an indefinitely large class of self-replicators, spanning a wide range of complexity, interconnected by a network of potential mutational pathways, including pathways from the most simple to the most complex. This is an important result, as prior to that it might have been conjectured that there is a fundamental logical barrier to the existence of such pathways, in which case, biological organisms, which do support such pathways, could not be machines, as conventionally understood. Von Neumann considers the potential for conflict between his self-reproducing machines, stating that our models lead to such conflict situations, indicating it as a field of further study. 147. The cybernetics movement highlighted the question of what it takes for self-reproduction to occur autonomously, and in 1952, John von Neumann designed an elaborate 2D cellular automaton that would automatically make a copy of its initial configuration of cells. The von Neumann neighborhood, in which each cell in a two-dimensional grid has the four orthogonally adjacent grid cells as neighbors, continues to be used for other cellular automata. Von Neumann proved that the most effective way of performing large-scale mining operations such as mining an entire moon or asteroid belt would be by using self-replicating spacecraft, taking advantage of their exponential growth. Von Neumann investigated the question of whether modeling evolution on a digital computer could solve the complexity problem in programming. Beginning in 1949, von Neumann's design for a self-reproducing computer program is considered the world's first computer virus, and he is considered to be the theoretical father of computer virology. Weather systems and global warming. As part of his research into weather forecasting, von Neumann founded the meteorological program in Princeton in 1946, securing funding for his project from the U.S. Navy. Von Neumann and his appointed assistant on this project, Jules Gregory Charney, wrote the world's first climate modeling software, and used it to perform the world's first numerical weather forecasts on the ENIAC computer. Von Neumann and his team published the results as numerical integration of the barotropic vorticity equation in 1950. Together they played a leading role in efforts to integrate CR exchanges of energy and moisture into the study of climate. Von Neumann proposed as the research program for climate modeling, the approach is to first try short-range forecasts, then long-range forecasts of those properties of the circulation that can perpetuate themselves over arbitrarily long periods of time, and only finally to attempt forecast for medium-long time periods which are too long to treat by simple hydrodynamic theory and too short to treat by the general principle of equilibrium theory. Von Neumann's research into weather systems and meteorological prediction led him to propose manipulating the environment by spreading colorants on the polar ice caps to enhance absorption of solar radiation, by reducing the albedo, thereby inducing global warming. Von Neumann proposed a theory of global warming as a result of the activity of humans, noting that the Earth was only 6 degrees Fahrenheit, 3.3 degrees Celsius, colder during the last glacial period. He wrote in 1955, carbon dioxide released into the atmosphere by industry's burning of coal and oil, more than half of it during the last generation, may have changed the atmosphere's composition sufficiently to account for a general warming of the world by about 1 degree Fahrenheit. However, von Neumann urged a degree of caution in any program of intentional human weather manufacturing. What could be done, of course, is no index to what should be done. In fact, to evaluate the ultimate consequences of either a general cooling or a general heating would be a complex matter. Changes would affect the level of the seas, and hence the habitability of the continental coastal shelves, the evaporation of the seas, and hence general precipitation and glaciation levels, and so on. But there is little doubt that one could carry out the necessary analyses needed to predict the results, intervene on any desired scale, and ultimately achieve rather fantastic results. Technological singularity hypothesis. The first use of the concept of a singularity in the technological context is attributed to von Neumann, who according to Ulam discussed the ever-accelerating progress of technology and changes in the mode of human life, which gives the appearance of approaching some essential singularity in the history of the race beyond which human affairs, as we know them, could not continue. This concept was fleshed out later in the book Future Shock by Alvin Toffler. Cognitive abilities. Other mathematicians were stunned by von Neumann's ability to instantaneously perform complex operations in his head. As a 6-year-old, he could divide two 8-digit numbers in his head and converse in ancient Greek. When he was sent at the age of 15 to study advanced calculus under analyst Gabor Szego, Szego was so astounded with the boy's talent in mathematics that he was brought to tears on their first meeting. Nobel laureate Hans Bethe said, "I have sometimes wondered whether a brain like von Neumann's does not indicate a species superior to that of man," and later Bethe wrote that brain indicated a new species, an evolution beyond man. Seeing von Neumann's mind at work, Eugene Wigner wrote, "One had the impression of a perfect instrument whose gears were machined to mesh accurately to a thousandth of an inch." Paul Holmes states that von Neumann's speed was awe-inspiring. Israel Halperin said, "Keeping up with him was impossible. The feeling was you were on a tricycle chasing a racing car." Edward Teller admitted that he never could keep up with him. Teller also said von Neumann would carry on a conversation with my 3-year-old son, and the two of them would talk as equals, and I sometimes wondered if he used the same principle when he talked to the rest of us. Peter Lax wrote von Neumann was addicted to thinking, and in particular to thinking about mathematics. When George Dotzig brought von Neumann an unsolved problem in linear programming as I would to an ordinary mortal, on which there had been no published literature, he was astonished when von Neumann said that, before offhandedly giving a lecture of over an hour, explaining how to solve the problem using the hitherto unconceived theory of duality. Lothar Wolfgang Nordheim described von Neumann as the fastest mind I ever met, and Jacob Branowski wrote he was the cleverest man I ever knew, without exception. He was a genius. George Polya, whose lectures at ETH Zurich von Neumann attended as a student, said Johnny was the only student I was ever afraid of. If in the course of a lecture I stated an unsolved problem, the chances were he'd come to me at the end of the lecture with the complete solution scribbled on a slip of paper. Eugene Wigner writes, "Janksy, I might say, is angular momentum always an integer of h?" He would return a day later with a decisive answer, "Yes, if all particles are at rest." We were all in awe of Janksy von Neumann. Enrico Fermi told physicist Herbert L. Anderson, "You know, Herb, Johnny can do calculations in his head 10 times as fast as I can. And I can do them 10 times as fast as you can, Herb, so you can see how impressive Johnny is." Halmas recounts a story told by Nicholas Metropolis, concerning the speed of von Neumann's calculations, when somebody asked von Neumann to solve the famous fly puzzle. Eugene Wigner told a similar story, only with a swallow instead of a fly, and says it was Max Born who posed the question to von Neumann in the 1920s. Von Neumann was also noted for his eidetic memory, sometimes called photographic memory. Hermann Goldstein wrote, von Neumann was reportedly able to memorize the pages of telephone directories. He entertained friends by asking them to randomly call out page numbers, he then recited the names, addresses and numbers therein. Mathematical legacy. It seems fair to say that if the influence of a scientist is interpreted broadly enough to include impact on fields beyond science proper, then John von Neumann was probably the most influential mathematician who ever lived, wrote Miklos Ridii and John von Neumann, Selected Letters. James Glim wrote, he is regarded as one of the giants of modern mathematics. The mathematician Jean Dieudonné said that von Neumann may have been the last representative of a once flourishing and numerous group, the great mathematicians who were equally at home in pure and applied mathematics and who throughout their careers maintained a steady production in both directions, while Peter Lax described him as possessing the most scintillating intellect of this century. In the foreword of Miklos Ridii's Selected Letters, Peter Lax wrote, to gain a measure of von Neumann's achievements, consider that had he lived a normal span of years, he would certainly have been a recipient of a Nobel Prize in economics. And if there were Nobel Prizes in computer science and mathematics, he would have been honored by these, too. So the writer of these letters should be thought of as a triple Nobel laureate or, possibly, a 3.5-fold winner, for his work in physics, in particular, quantum mechanics. Illness and death. In 1955, von Neumann was diagnosed with what was either bone or pancreatic cancer. He was not able to accept the proximity of his own demise, and the shadow of impending death instilled great fear in him. He invited a Roman Catholic priest, Father Anselm Strittmatter, OSB, to visit him for consultation. Von Neumann reportedly said, so long as there is the possibility of eternal damnation for non-believers, it is more logical to be a believer at the end, essentially saying that Pascal had a point, referring to Pascal's wager. He had earlier confided to his mother, there probably has to be a God. Many things are easier to explain if there is than if there isn't. Father Strittmatter administered the last rites to him. Some of von Neumann's friends, such as Abraham Pais and Oscar Morgenstern, said they had always believed him to be completely agnostic. Of this deathbed conversion, Morgenstern told Himes, he was of course completely agnostic all his life, and then he suddenly turned Catholic. It doesn't agree with anything whatsoever in his attitude, outlook and thinking when he was healthy. Father Strittmatter recalled that even after his conversion, von Neumann did not receive much peace or comfort from it, as he still remained terrified of death. Von Neumann was on his deathbed when he entertained his brother by reciting by heart and word for word the first few lines of each page of Goethe's Faust. He died at age 53 on February 8, 1957, at the Walter Reed Army Medical Center in Washington, D.C., under military security lest he reveal military secrets while heavily medicated. He was buried at Princeton Cemetery in Princeton, Mercer County, New Jersey. Honors Selected Works, 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 Mercer County, New Jersey.